Welcome to Ask and Learn.
In this problem, we have a table, and again, there's a much better illustration in the book. A table, or a circular table here, that's supported by wires attached at three equal spacing at equally at 120 degrees apart. And so then they basically, this platform hangs from these cables, and we get that if we twist this, then these cables actually wind up kind of shortening a bit, and the center of mass will rise up, and then there will be a restoring force trying to untwist it, and so you would actually get some kind of back and forth motion if you twisted this thing. Now, let's see here. We know that the tension in the cable is mg over 3. So the mass of this cable divided by 3, since there's 3 cables. Now, again, that is assuming that we have very, very small motions of the center of mass here, of the center of mass up and down. Okay, so it's a little bit strange in the fact that, you would think that it's actually the fact that this thing is moving up and down that's causing it, and that's true, but it's also the fact that when you twist this, the tension in the wires and the cables would provide a restoring force. So if we make some assumptions about that the change in height as we rotate this. So again, if we take a look at one cable and we have the bottom here of the plate, and then we take a look at this, and the cable length is assuming to be this constant. So this would have to rise up a little bit, but we're going to assume that that is a minor effect. Okay, because the length is roughly the same, because this angle is very small. Okay? Otherwise, we could figure out what that was. I mean, we could actually get the nonlinear equations, but it's going to wind up being a higher order term that would involve, say, theta squared. So our tension is static in the first approximation. So if we do moment balances about the center of mass of this platform, we get minus 3 RT phi, where phi now, and why it is phi is that's because we need the component. If we look at the platform here and the wire here, we need the component in the direction perpendicular to the edge of the disc here, and that component is t sine of phi, or roughly t times phi, where phi is now the angle from the vertical to the wire. Okay, so I hope you can see that. That's not the same as the angle theta here, although they are related. So anyway, we get that minus 3 RT phi equals J theta double dot. Now, phi and R are related because if you think about, this thing was over here, and it moved this amount here. So let's say that is the motion, and so this is phi. So this distance is approximately L times phi, and then the same distance, if you look at it from here, is R times theta. So that those two things need to be equal, at least to our first approximation. Yeah. So then we can then take this and eliminate phi, and then put this in for t, and we get J theta double dot plus and then R RMG, well, R's cancel out, so we get mg over L theta equals 0. J is 1/2 mr squared, because this is a uniform circular disk. Plugging all that in, and we see that the m's cancel out, we get an r squared cancel out, and we get the natural frequency is simply 2g, square root of 2g over L. So again, it's interesting that R doesn't matter, but L does. So again, and that's kind of what we'd expect from a pendulum, since this is kind of like a pendulum, at least when we have gravity as our restoring force. And then we get the natural period is 2 pi times square root of L over 2g. So again, this is a much more complicated problem if we didn't assume that these angles were small. And even if you've probably had a situation where you maybe played with something that was attached and you twisted it, and then you can see that what happens is this plate comes up, and it basically will hit the bottom when these wires are vertical, and then bounce back up. So again, it basically the plate, this surface here, goes through 2 cycles for every cycle back and forth it goes. And I'll just let you think about it to convince yourself, because as it goes here to here, as it goes theta goes from here to here, the elevation goes up and down, and then it goes from here to here, the elevation then goes up and down. So there's 1 cycle, and that's 2 cycles, but we only went through 1 cycle of the rotation. So again, and you can also see that when you do this thing kind of hit the bottom, and it kind of usually jars things. So again, you can play with a system like that, but it's actually very, very nonlinear.